Direct variation was two quantities related by a constant ratio. Now, inverse variation is two quantities related by a constant product. Those two quantities are inversely related. This means when one of the quantities increases, the other quantity decreases. And when one of the quantities decreases, the other quantity increases. This relationship may be expressed with the following formula. So, these products. It may more easily be understood by the following example. Consider this table of data. We have x and y with the given values. In this table, x and y are inversely related because the product y times x is always 12. They're related by a constant product. 3 times 4 is 12, 1 times 12 is 12, and 2 times 6 is 12. Thus, x and y are inversely related. Pulley system relationship. The relationship of two rotating pulleys connected by a belt is an example of inverse variation. This relationship may be expressed with the following formula. The diameter of pulley A times the rotations per minute of pulley A is equal to the diameter of pulley B times the rotations per minute of pulley B. The diameter of a pulley is inversely related to the rotations per minute of the pulley. Example 2. A pulley 32 inches in diameter turns at 825 rotations per minute. At how many rotations per minute will a pulley 25 inches in diameter turn? We have diameter A equal to 32 inches and rotations per minute of pulley A equal to 825 rotations per minute. We're also given that the diameter of pulley B is 25 inches. But we don't know what the rotations per minute of pulley B is, so we'll call it x. Then we'll use our formula for a pulley system, plug in the known information, and solve for x to find the rotations per minute of pulley B. It's really just determining the right formula to use, plugging in the known information, and then solving to answer the question. So here we would multiply 32 and 825 and then divide by 25 to get x equals 1056. So pulley B turns with 1056 rotations per minute. Gear system relationship. The relationship of two rotating gears is an example of inverse variation. This relationship may be expressed with the following formula. The number of teeth in gear A times the rotations per minute of gear A equals the number of teeth in gear B times the rotations per minute of gear B. The number of teeth of a gear is inversely related to the rotations per minute of the gear. If there's more teeth, then there's less rotations per minute, and if there's more rotations per minute, then there's less teeth. Example 3. A large gear with 180 teeth running at 600 rotations per minute turns a small gear 900 rotations per minute. How many teeth does a small gear have? So we have that gear A has 180 teeth and rotates at 600 rotations per minute. We have that gear B, we don't know how many teeth, so we call it x, and the rotations per minute of gear B is 900 rotations per minute. We'll plug all this into our formula. Notice it's two products, as it should be for inverse variation. Plug all this in to our formula, what we know, and x for the unknown, rotations per minute of gear B, and then we just have to solve to find those the number of teeth, the unknown, for gear B. So multiply 180 times 600, divide by 900 to get x equals 120. So the small gear has 120 teeth. Lever principal relationship. The relationship of a lever pivoting on a fulcrum point, this thing, is another example of inverse variation. This relationship may be expressed with the following formula, where F is the force and D is the distance. So we have a lever here. On each side there's some force being applied and a certain distance between those forces and this fulcrum here. The relationship of these two forces and their distances is inverse variation. The amount of force required is inversely related to the distance from the fulcrum. Example 4. A piece of machinery weighs 3 tons. It is to be balanced by 2 men whose combined weight is 330 pounds. So those are our two forces. The piece of machinery is placed 11 inches from the fulcrum. Not very far. How far from the fulcrum must the 2 men exert their weight in order to balance it? So on one side we have the 3-ton piece of machinery. On the other we have the 2 men weighing 330 pounds. So one force of 3 tons. Notice that one of our weights measurements is in pounds and the other is in tons. We need to be in the same unit of measurement. So we're going to convert the 3 tons to 6,000 pounds since there's 2,000 pounds per ton. That way we have both our forces in units of pounds. We also have that the distance to the machine is 11 inches from the fulcrum and the force of the 2 men is 330 pounds. We'll plug all this information into our formula for the lever-principal relationship, leaving the distance that the 2 men are from the fulcrum as the unknown. So that's our x. Plug all of this in. Then we just have to solve for x to find how far the 2 men are from the fulcrum. We multiply 6,000 times 11, divide by 330 to get 200. So the 2 men must be 200 inches from the fulcrum.